Hello, my name is Erin Krupa, and I'm an Assistant Professor of Mathematics Education at Montclair State University in New Jersey. Today I'm going to do a close reading of a mathematical task and relate it to the key tenets of mathematical literacy. So we're going to read this like a mathematician would. This excerpt comes from Core Plus Mathematics textbook, Course 2. It was created by the Core Plus Mathematics project with money from the National Science Foundation and is now published by McGraw-Hill. Drilling teams from oil companies search around the world for new sites to place oil wells. Increasingly, oil reserves are being discovered in offshore waters. The Gulf Oil Company has drilled 2 high-capacity wells in the Gulf of Mexico, 5 kilometers and 9 kilometers from the shore. The 20 kilometers of shoreline is nearly straight, and the company wants to build a refinery onshore between the 2 wells. Since pipe and labor cost money, the company wants to find the location that will serve both wells and uses the least amount of pipe when it is laid in straight lines from each well to the refinery. Notice the real-world context of the task. This is based on real-world data and can be tied to other content areas and implications for society, environmental impact, historical significance of oil refineries, health and safety concerns. A mathematician might begin to visualize these oil reserves at the very beginning of the task, when the text read, drilling teams from oil companies search around the world for new sites. Increasingly, they're being discovered in offshore waters. So the visualization of the wells lying in offshore waters can come right at the beginning of the text. This is the beginning of mathematical modeling. Then the text goes on to say that they have drilled 2 high-capacity oil wells in the Gulf of Mexico, and they introduce the numbers 5 and 9 from the shore and the 20-kilometer shoreline. So we might begin to visualize these 2 oil refineries in the middle of the ocean. One is 5 kilometers out and the other is 9, and then there's 20-kilometer shoreline between them. We need to locate a refinery on the shore between the 2 wells, but we don't have any restrictions yet. We could mathematically represent the 2 wells and the given distances, and we could construct our own models and representations based on our interpretation of the problem so far. As we continue reading, some more constraints are entered into the text. Since pipe and labor cost money, the company wants to find a location where they can put the refinery to serve both of the wells. Now the problem is posed. We want to save money on the pipe and the labor. A mathematician would read this as we want to minimize the distance between the 2 wells and the refinery, located some distance between the 2 wells on the coastline. So an answer isn't automatic in this problem. A mathematician might start with a pictorial representation of the scenario, and the representations that each mathematician might come up with would be different. If you think geographically about where the Gulf of Mexico is located, you might come up with a different picture than if you were orienting it in terms of your body and hand positioning. The task goes on to ask, how can coordinates be used to model the situation? Depending on how you drew your mathematical model, it might vary the coordinates that you use, and that's okay because there can be different answers to the same question. What distance should you try to minimize to use the least amount of pipe? So this question is about the distance between the wells, the refinery, and how much pipe it would take. So that's what we want to minimize. And it's important that we understand that minimize means we want to make that the smallest we can. The third question is, do you think the refinery should be closer to A, to B, or to the midpoint of the shoreline? Make a conjecture. A key tenet of mathematical literacy is making hypotheses and then testing them out. So here we make a conjecture and then students would engage in testing it. The fourth question is, determine your best estimate for the location of the refinery, about how much pipe will be required. And here's where we actually solve the mathematical task. It's important to realize there are multiple points of entry into this task. Several methods for solving this problem include analyzing tables or graphs of a function relating to the total length of the pipeline and the distance to the refinery. So this would be an algebraic solution. You might use point D and its reflection across line BC and congruent triangles. This would be a geometric approach to this task. Or you could use click and drag features of geometric interactive geometry software. This technology can provide an infinite amount of data points in a really quick time frame to test conjectures and refine hypotheses before students engage in a solution. Each of these reasoning strategies is valid and allows for different models of representation to be utilized and different symbols to be used. To be mathematically literate means to use mathematical reasoning to arrive at a solution and to move flexibly among different representations and interpret the solution strategies of others. So it's important that students would create their own mathematical arguments for how they approach this task. This has been a close reading of the oil refinery task from Core Plus Course 2 textbook. Thank you for your time.